Um, I wanted to, as I I wanted to begin with some comments on the material we saw yesterday, and then talk about what's anticipated for today. So, ladies and gentlemen, yesterday we had a quite full day on three major topics. In the first little bit, we took a model that we built from scratch, and we used it to examine the effects of networks on both the structure of the network, as summarized by a measure of degree centrality for individuals, and on the dynamics of that network in the form of the spread of infection through that network. So we saw that any logic can support predefined network types very readily for a substantial class of a set of different classes of networks. So on the extremes, very local networks, things like ring lattice and 2D distance-based network. That's 2D locality on the one hand for the ladder, and 1D for the ring lattice. It could also support very global networks. The classic example being Poisson random network, also called Erdos random network or Bernoulli network. This is a network where any two people, no matter where they're located in space, where they're located compared to each other within the depiction of the network, they're equally likely to be connected. They have a certain probability of being connected, any pair of individuals. So there's no locality at all. People are connected willy-nilly with each other with a certain probability. And also mixtures of the two in the form of a small world network, a network which is largely local. Often it's something like 90 or 95% ring lattice, and 5% of connections, however, are global. And this captures the fact that many of our social connections, for example, are with people nearby us, but often we have a few connections with people far distant. And small world networks have been the subject of some very interesting work 1 or 2 decades ago by Duncan Watts and Steve Strogatz, who showed that even just those few long distance connections can often make a huge impact on network dynamics. AnyLogic also supports another very interesting theoretic but quite practical network type called scale-free network. And these are networks that exhibit power law scaling in terms of the number of connections that people have. So no matter how many if we consider someone with k connections, no matter how big k is, the probability of having k connections compared to 2k connections, it's always the same ratio of probabilities. So this means it has a very long tail. Most people have few connections, but some people have a large number of connections. And as we see, as you'll find out if you read the literature, there's a large number of networks out there, from sexual networks to networks associated with mixing patterns, people's contact, to aspects of the structure of engineered systems like the internet, which exhibit power law scaling, and which can be well described by scale-free networks. So they are of considerable interest, not least because the individuals with large numbers of connections, the hubs, have enormous influence, both because if we consider a pathogen, an infection, or if we consider spread of ideas, they're both more likely to get that contagion, because they have a large number of connections to get from, and more likely to pass it on to a large number of people. So scale-free networks are of great interest because they can capture this great heterogeneity in terms of number of connections, which can have a hugely disproportionate impact on the dynamics of the network as a whole. And where you can get the situation where the tail wags the dog. A small number of people, a small segment of the population, maybe 5%, wields a disproportionate influence on the dynamics of the whole network, and far disproportionate, may shape, the fact that the infection lives on in the population rather than going extinct. So scale-free networks are of great interest, and they're well supported by any logic. But more deeply than that, to that last example we saw in the closing minutes of the morning, we actually saw that we can craft network connections ourselves. I don't know if you remember, but the next thing we went on to was open populations, and I'll come back to that in just a moment. But one of the things we did is we hitched up explicitly a connection between a mom and her child, for example. And also when new people came into the network, we knitted them into the network. So networks in any logic are not static quantities, rich though they may be well supported by the different network types. They're dynamic quantities, and more than that, you can actually custom define the connections that you want. And one of the example models that I've given to you and highlighted in that folder for of particular note is a model which reads network structures from files, say from a PIAC file, or from another type of file that defines dynamic networks, and can impose them in any logical model. So it can create a network based on any network structure you specify to it from a file. And it's not a hard thing to do. AnyLogic supports these mechanisms for saying A, connect to B, or disconnect from B. And it provides very easy ways of saying, find me all people within a certain distance of A, for example, and then you can go add connections to some of them, etc. So, although we didn't have time to go into it, networks in AnyLogic are well supported for a classic set of network types, but then also can be custom built very readily. In the area of open populations, we took that same basic model and we added into it a set of 4 processes. The processes were immigration, so people could join the model with certain distinct characteristics, and they'd be added to the model. And we did that via an event which took place, which was firing off in main. It was in main because there was no existing person already there for it to fire off, and so we had it fire off in main at a certain rate, number of immigrants per unit time, per year, say, and at that rate it would create new people. But we also had, beyond that, the capacity to represent births of individuals and deaths of individuals. And the mechanisms to characterize that were undertaken within each person. Why? Because it's a person who's subject to, say, giving birth, a person who's subject to death, and therefore those mechanisms were associated with a person. Each person had a mortality rate. And that mortality rate and the fertility rate might in general be affected by that person's characteristics, by their age, for example, by the comorbidities that they suffer or what have you. So we saw that we could easily encapsulate those mechanisms within a person and have people coming into the population for sure, but people dying as well, people giving birth. And the mechanisms that we used, while very simple, were designed to allow us to capture the heterogeneity in terms of people's characteristics and history, and as much as they might shape rates of fertility or rates of mortality, etc. So open populations are well supported in AnyLogic. How did we support them? Well, there were 2 basic mechanisms. One is to add people to the population, whether due to immigration on the one hand or due to births on the other. We needed to tell the population in main. We needed to tell main, add somebody to this population. And when we added them, we needed to tell it what characteristics to give to that person, and specifically what values to assume for the parameters for that person. Because remember, those parameters encode the assumptions about that person, and they communicate them to the person when they get created. So we put in place this mechanism which would call off to this thing called add underbar in the population name. In our case, it was add underbar population, but if your population had been called pop, it would have been called add underbar pop. And that allowed us to add these people to the population. And when someone died, there were two basic ways. We could say delete self, which has some limits to it in terms of if that person's also in a discrete event model, or we could say remove underbar population name, and then they'd be removed from the population. And we did see that in the context of networks, we needed to have in place a mechanism that when someone joins the population, we can weave them into the network. We can update the network to have them be present within it. And AnyLogic had some strong abilities to do that, but we discovered a bug in the model because we asked it to update the wrong network. We asked it to update the network of the person, where really we wanted to update the network as a whole. Now, in that debugging process, I wanted to highlight the fact AnyLogic has a set of mechanisms for tracking down problems. And I haven't really emphasized those that much, but one of them that you're going to rely on heavily is what's called the problems window. Okay? And if you have a problem in the model that is immediately visible to AnyLogic, it will be visible within the problems window. So I'll just open up one of these models. This happens to be the model from yesterday afternoon. And I'm going to deliberately introduce a problem. Okay? So what I will do is I will go to a population size, and I will do something like this. Boom. And by putting a space there, if I try to build this model or try to run this model, it's gonna exhibit displeasure. Okay. I could try to run it from here, and we'd see a similar thing. Try to say run, go run, and it'll say, essentially, I don't understand what you're trying to get me to do. That's its way of saying it. It's not very loquacious in making that statement, but that's what it boils down to. It doesn't know what we mean. It can't understand our request in the model. It doesn't understand our specification of the model. And it says, do you really want me to run this model with the old version? In other words, proceed with launch? That would be basically, it would run the old version of the model. And if you say proceed, you'll be running the old version of the model, not the model that you like it to run. So normally we would cancel here. Do not check that box, or else you will find yourself confused. But generally we cancel out. If I see this, I generally cancel. And then I go and repair to the problems window. Now this window might not be visible for many of you, but you'll notice down here, there's this thing called 2 errors, this thing that reports the number of errors. And if you click on that, you'll see that window. Or as windows in general, you can go and request that it be shown here. Okay. So the problems window. Okay, interesting. Yeah, here it is. Boom. I can hide it, and I could show it. Okay, now it behooves you to understand how to interact with this problems window. Probably the key factoid. There's a couple key factoids. This window is like a good friend who tells you the difficult truths you need to hear. Okay. And you may have a love-hate relationship with it, because it's going to tell you things that are painful sometimes, like it doesn't know what in the world you mean. But it's important, by the same token, to view it as your friend. It's designed to help you discover problems in your model so that they don't just get brushed under the rug and corrupt your results, and you find that that paper you published in, you know, PNAS or something on these really interesting discoveries all turns out to be all wet because the model is broken. This problems window will spot problems for you and alert you. So it's good to have a healthy emotional relationship with it. The second thing is sometimes it shows you a whole set of things which really boil down to one thing being wrong. So don't get overwhelmed. Just because it shows you 10 things doesn't mean there's 10 things wrong. Maybe there's one thing wrong, it's just getting terribly confused about that one thing. It's being thrown off hugely about it because it gets really puzzled about what's going on. So let's go see. Here I caused one problem, but you notice it gave me two problems, right? Or it listed two problems. These are really just different sides of one problem. But the key thing is, double click on this guy and it will bring you to what it's confused about. What has thrown it off? And it's not always perfect in this regard. Sometimes it's out to lunch where it brings you. But about 90% of the time, I'd say it's on the money. It'll bring you to the thing that's confused about. And you'll notice that there's several hints here. First of all, you know, if you click there, often it brings it up in the properties window. Second of all, you'll notice there are these little X's. And X marks the spot, ladies and gentlemen. It marks the spot where there's a problem. So what this is saying is, in this place, within agents, within main, within the model as a whole, there's a problem. Okay? And so, you know, you may double click there. It says it's associated with the population. Indeed it is. But, you know, one of the best ways is to just go take it from the properties window. And having done that, ladies and gentlemen, I'll see something might be wrong. And if I try to fix it, then I'll go back, save, build, and now it's a happy camper. Okay? Ladies and gentlemen, this window for problems is one of the best ways of heading off mistakes in your model. So listen to it carefully. A few other pointers though. If you have multiple models loaded, let's suppose we loaded in this guy as well. It's going to actually, by default, if we build, it may actually in some cases build with respect to multiple models, okay? In which case it may actually show in the problems window results from other models that you're not so interested in. And there are ways of dealing with that. There's ways of restricting it to only show from one of the models. And one of the ways is that you could tell it filter problems by a certain model or filter problems by the area of the model that I want to look at. This will also show warnings, which is a good thing to look at. Maybe it's warning you. Something looks kind of weird here. I'll take it at face value, but it looks strange. And you might want to be aware of that. Okay? I would have this option selected, view automatically when there are any errors. Okay? So the problems window is one of the best ways to spot issues with your model. And if it's complaining, you really got to deal with it. And if you don't understand what's going on, try clicking on things and try going to where it points you. Now, sometimes that's not enough. Sometimes it lands you in a weird situation. I could probably try to create one of these situations. It takes a little bit of creativity, but I could probably create a situation where it is so whacked out that it doesn't know where to point me. Give me a second here. I'll try doing something kind of wacky here. Let me just try inserting strange things here. Okay, let's see if it's going to catch this. Okay, yeah. Okay, so yeah, it actually caught that. Okay, AnyLogic's gotten better, I guess, in that regard. Let's try doing this. How to for immigration rate.
I put in like a semicolon in the middle of it. Will it get confused? Oh, look at this. Okay, okay. No, it's pretty good about bringing that. Okay, that's good. Sometimes what happens is it brings me to the middle of the code. It brings me to the middle of the code that's behind this. And may I show you something now that I've been keeping from you? May I show you something that I haven't wanted to scare you with? Kurt, go lock the door if you could. Okay, ladies and gentlemen, if you go look at this model, I've just compiled the model correctly. I've removed my affronts. But if you go look at this, you will find that, well, actually, maybe I'll make one more attempt. Watch this. Okay, this will be an interesting one. I'm going to put a end curly bracket there. This might throw it off. Oh yeah, okay. Okay, no, it's still a happy camper. Okay, okay. Let's see if we can get it. Ah, there. Okay, okay. We're cooking with gas now. Okay, there we go. Yeah, this is what it gives me. If you folks have been working with AnyLogic under Tiffany, for example, great to see you. So you may have seen this before. This is one of the cases where AnyLogic fails to show you with clarity what's going on, okay? It gets terribly confused. And let's go see what actually happened. What I put was seemingly innocuous. I put a curly bracket here. This might have resulted from a typo. But it takes this to indicate it's the end of some logical bunch of code here. And then it gets terribly confused by what's after that. It turns out curly brackets are used in Java to distinguish the beginning and end of, amongst other things, methods or functions. So this is the beginning of a function, this is the end of a function, it thinks, and then it gets confused by what's here and by this other one, and it just throws you into the code. This is the code that lies behind this model. Now, the good news is you don't have to futz with this code. In fact, you're not allowed to modify it. This is generated automatically as part of the process of getting it ready to run this model. But sometimes you end up, despite your best intentions looking at this code, it puts you in here because it doesn't know what to do. And if you've got a problem like this, may I make two suggestions, okay? One of them immediately actionable, one of them an investment for life, okay? The immediately actionable suggestion is to do the following, okay? The immediately actionable suggestion is to not just throw your hands up, but go, you notice this occurred for one of these things. It brought me here. But if I go click on some of these others, okay, that didn't help that much. Let's try this one. Okay, now it's giving me something else that might alert me. Oh, there's this weird character there. There's a weird character there. I wonder why that is. And that might alert me to go actually say, oh, I recognize that code. That code, I don't recognize some of the stuff around it, but I recognize that. That's something to do with my immigration, and that's in that immigration event. And then I go look and I say, oh, there's this thing here. I can get rid of that. It's a typo. And then try building again, building the model again. Yet others of these, if I go, it'll actually bring me to the place directly where the problem is. So when you have this cascade of errors, this is one error. Conceptually, this is one fault in the program, but it's causing a cascading series of 5 of these. So this is why I'm saying don't get overwhelmed. It doesn't mean there's 5 errors in your program. It could be one error, and don't overly interpret any one of these mistakes and focus at the exclusion of others on that one. Poke around and see if some of these might actually be more insightful than others and clue you in to what's going on. Okay? So I would suggest having a bit of patience and looking at what it's showing you, keeping track of these windows. Okay, that's one thing. I'll list three, actually. The second thing, ladies and gentlemen, if you're having this problem in a persistent way, it's to save this model. Take a copy of this model so you can modify it without worrying you're going to destroy the original model. And then you can start to disable things or rip out things that you've added recently, so that you can narrow down where it might be, what might be causing it. For example, if you recently modified this component of the model, immigration event, you might temporarily ignore it. And this is a very useful thing in any logic, because if you tell it to ignore it, well, okay, it's throwing a hissy fit. Okay, so okay, that's okay. What did I do? This is really interesting. Okay. Okay. Oh, okay. I must have done something bad here. Okay, this is a great little example. Okay. Okay. So what am I doing here? You're watching me in action. Okay. This is a great little lesson. Something's gone wrong here. Something's gone terribly, terribly wrong with this lecture. It's causing about, 10, 15 maybe, 15 to 20 errors? Okay. So this is going to be fun. Something's wrong. I don't know what's wrong. But what do? I start with saying, I'm going to create a hypothesis. My hypothesis, I did something silly, and I thought I was disabling the event, but I really disabled all of main. I meant to check this with ignore, to say ignore the immigration event, but I'm wondering, maybe I did it with main as a whole. Okay, main as a whole is not ignored. Okay, the plot thickens. Okay, great. So what did I ignore here? What did I tell it to ignore? This is why you copy your model before changing it. Okay, so let's go see here. Main cannot be resolved to a type. Okay, this is looking really interesting. Main cannot be resolved to a type. Okay, it's freaking out about main. Okay, let's go figure this out. Okay, so what did I do? It doesn't understand main. Okay, so one hypothesis is that main has some error in it that's causing it to not understand main. I don't see any evidence of a current error in main. But I remember I disabled something, and I thought I was disabling this immigration event, but I must have disabled something else. Let me do ignore immigration event, see what happens. Now, builds completed successfully. Okay. Now we're cooking with gas. So just ignoring this totally fixes the problem. Okay, I unignore it, and now it's showing me all of this. I ignore it, and
there's no main problem.
Now there's no main problem. Yeah, mumble. Okay, but if I ignore this, the problems go away. If I unignore it, the problems are present. That's a sign that maybe this is an issue. But really, I should have saved this away to a separate model so I could then start to rip things out. I could start to change things. So I should have called it, for example, model debug. Called it debug model. And then I could actually, if required, totally ignore this, and I don't have to worry that I'm screwing the model all up. I could delete a parameter that I've recently added. I could eliminate a new chart, and I don't have to worry that I'm throwing some value away that I'm going to have to add in later. I've got the original model saved away. Once I learn what the problem is, then I'll go back and fix it in the original model. But in the meantime, I can proceed with abandon to investigate the problem here by throwing things out and disabling things without having it hang over me that I'm going to lose valuable information. Okay? So when you have a problem, don't panic. Systematically experiment. Develop a hypothesis for what might be causing that problem. Use the problems window. But the ugly truth is, ladies and gentlemen, the ugly truth is that not all problems are of this type that I'm showing. Not all problems, your trusted friend is going to tell you that, hey, there's a problem. Oop, there's a problem here. There's going to be some problems, ladies and gentlemen, which are not visible until you run the model. This problems window is going to spot problems where it doesn't understand what you're trying to tell it to do. It's almost as if it's kind of like spotting grammatical errors in a article. So, you know, I have students from across my group who give me articles, you know, at first draft or something, and you know, often I'll first look for grammatical issues and spelling and so on, and work on those. And I don't really have time doing that to engage with the underlying ideas. Or imagine if I gave you an article on computer science I wrote about, you know, some software design for an environment to perform modeling. You might understand something about the domain context, but a lot of the software engineering components and computer science, you might not understand, but you could spot a grammatical error. You know, if it says something like, we distribute the computation over multiple machines, you'd say, that doesn't sound right. That there's a case problem there. It should be we distributed or we work to distribute or something like that. So any logic's problem window is to spot essentially grammatical errors, cases where it doesn't know what you're meaning to say. But it's not going to allow it to spot the semantic errors that are more sophisticated, where you're doing something in the model, you specified it in a certain way, but it's not what you wanted it to be specified as. It's not going to understand where there's a difference between what you wanted to do and what you told it to do. It's just going to listen to what you told it to do. So those sort of errors include the mistake I made yesterday, where I said basically apply the network to the person. I meant to say apply the network to main, but I actually told it to apply the network to the person, to the mother. And as a result, it did something that was unexpected. It didn't knit the baby into the new baby into the whole network. And I was surprised by it. And I had to undertake a process called debugging, where we went and found it. Now, good news and bad news. The good news is there's a science to debugging. And there's orders of magnitude difference in how quickly people can find problems based on a tried and true method of debugging. Forming a hypothesis, going and investigating the hypothesis, testing it out, and that process is more or less independent of your training in computer science or software engineering, etc. It's something that anyone can learn to apply. But it's not a trivial process. It involves working with the model in a careful way, observing, thinking about what could be causing this, and trying things. And the first rule there is very similar to what I told you just a minute ago. Make a copy of the model. Do not try, if you start getting stuck in debugging, you're trying to find this problem, don't try to fix it on your original model or you'll be handicapped. Either you will be restricted in what you throw out because you say, oh, I don't want to damage the model, or you will throw things out and have to recreate them later, and you'll be in a world of hurt because you'll forget how to recreate them. So make a copy of the model, debug, and then you can, again, toss things out, particularly the things you recently changed, the things that might be contributing to this error, or you'll go in and change them and say, does that make a difference? Does this help things? So you want to experiment. So my wife is a MD, PhD, and before she got her MD, she got her PhD in toxicology. Basically, it's a branch of chemistry, and she and I have very different styles in different areas of life, including in the kitchen, partly because her training, both medical and in the wet labs, taught her to be very cautious about experimentation. You know, everything is carefully aliquoted out. It's very carefully controlled experiment and so on.
you don't experiment. Hey, let's try this with this because you produce phosgene gas or some other toxic event happens or an explosion happens. In computers, you can experiment with abandon. And if you look at Kurt, one of his first reflexes, let's try it. Let's try it out. Well, that's an interesting area. Let's see that. And so, if you save your model as a separate version of the model for debugging, then you can try things very readily without worrying that it's going to hurt your model. You can rip things out, you can disable things, you can put in statements. Now, in that last point, I want to make this statement because that's one of the ways that I worked to track down yesterday's bug. One of the key things is to add statements into your model, to print things out. And I taught you yesterday this trace ln statement. Does anyone remember what this does? Yeah, it prints whatever. And just knowing I have reached this point, just printing that thing, or just printing number 1 sign, can be really useful to know, is this place ever being reached? Am I even getting there? In other words, is immigration occurring? So when I run this model, I might wonder, is immigration occurring? So one hypothesis, immigration in the model is not occurring. This event is never being triggered. Another hypothesis, well, it's being triggered, but it's not having the effect I thought it would. And by putting in a trace ln statement, we can then run the model, ladies and gentlemen, and we could go see, okay, is that statement in fact being printed out? Okay, so we're running the model here, and we will run it at full tilt, and we will go view in the console, and so, okay, there it is. It's saying I'm at number 1, so we know that we reached that point there. And this is the sort of thing you can do with the debugging version of the model, and you won't have to worry, I have to go strip all those things out, I have to remove them or whatever. It'll help you track it down. At other times, we print out information that can be very, very helpful for interpreting what's going on, such as reports, who was born to whom, etc. So trace ln statements can be very useful to get a sense of what's happening, what's not happening in the model, and to track down, what's going wrong. But they typically used to provide evidence towards a hypothesis that you might have that, maybe this is broken or maybe that's broken. Maybe what's happening is that this just isn't showing, but it's really there. An example would be you don't see a network, and one hypothesis is, well, there's no network. Another hypothesis, there's a network, but it's just not showing. And you can use trace statements to sort of distinguish those cases. So trace statements are one of the key tools for debugging. Now, I want to get into GIS, and I don't want to belabor this point long, but I will note that AnyLogic does have, in the professional and I believe the university researcher edition, what's called a debugger. Now, there's good and bad news here. The good and bad news is that this debugger the bad news is that debugger will not find your problems automatically. It will not say, I found your problem and fix it for you. The good news is it may help you fix it by allowing you to more easily trace down what's going on, by printing out when things happen, for example, by stopping it at certain times, etc. A debugger like this is extremely powerful, but it can be a bit daunting to learn to use the very first time. It can be difficult to sort of to learn how it works. An example would be, I can set, associated with a transition, this transition here for birth, I can set, ladies and gentlemen, what's called a breakpoint here. And this breakpoint basically provides a way for me to stop the model when it gets to this point so I can see what's going on. And I can even go step by step by step to see things as they're happening. So, I could continue this model here, and this model will be running, and
and I will go right here. This is the model where births were occurring after a gestational period of around 270 days. And you'll notice it just stopped there. It just triggered that breakpoint. I'm at person line 399, which turns out to be that location where I'd marked that breakpoint. In other words, stop if you hit this point. And this point is at that point where the mother is giving birth to the baby. So having done that, I can then step by step, I can go through this. So I can say, okay, here's the mother, and the mother refers to a certain person, and I can go in and see her characteristics. For example, I could see whether she was initially infected. And by executing this step by step, I can go see what's going on. Okay, so here's the baby. Who is the baby? I can go explore who the baby is over here, go check their characteristics, and I can go, and in fact, I can evaluate things like this. I could say, okay, print out for me the value of this expression. So the mothers get X value. I can, in fact, sort of go and say, okay, what's the current value of that? And see if I can piece together what might be happening at this point. This is very, very powerful. It allows you to stop at certain points where problems are about to occur and check out what's going on at that time, ask questions within the model. And you will note that there's this expressions window where I can actually go and I can add an expression for it to evaluate. For example, here's the mother's get X position right now is 140.6, okay? So it allows me to sort of zero in on a place of the model where I think trouble's about to happen or where it may be happening and actually interactively explore this. But this, ladies and gentlemen, gets me to the final recommendation, which is a lifelong one. And that is, you need a buddy. You need a buddy. And the buddy you need is a geek. So you need a geek buddy. Everyone needs a geek buddy, including geeks. If you could befriend someone who knows a little bit about programming and a little bit about Java, you can go much faster with things. They may look strange and they may act strange sometimes, but geeks are, they're often fairly approachable folks, and they're often more interesting than you think by looking at them. So if you can find someone who has some willingness to work with you, and they're from that other background, often they'll find it quite interesting, and they can help you overcome these bumps. They can help you get beyond those really weird error messages. You're not sure what's going on, those problems where you're really flummoxed. Find the Geek Buddy. Now, we are trying to set up a service to match Geek Buddies with others, and that service is in its nascent form. But right now it's very informal, but we're working towards a more sort of a Tinder for Geek Buddies or something like that. We're not there fully yet, but we're working on this. And if you can find a Geek Buddy, they will help you get more quickly beyond these things. And these sort of debuggers, these are tools we geeks use on a frequent basis, and so they can help you use it to greatest effect. If there were interest in this, I could give a whole lecture on debugging and so on, but those are some points ahead of time, because good models go bad sometimes. Sometimes bad things happen, and it's hard when you're first engaging with this to have a sense as to how big an issue it is. Is it a tiny thing or a small thing? Don't panic. Form hypotheses about what may be going on. Investigate them systematically. Don't assume just because there's a ton of things being complained about that there's a ton of things wrong. It may be one
sort of weird thing that it flips out about. Use the tools available to you, especially the problems window and trace LN that will print out where you're at. If you are feeling comfortable with it, try experimenting with the debugger if you have access to AnyLogic's debugger, and find a geek buddy. One thing I will say about the debugger, so this may shock you. I've spent probably hundreds, maybe thousands of hours in debuggers in my life. I've used them extensively for software development. Probably for AnyLogic, I use it about once a year. I do a lot of AnyLogic debugging, and mostly I don't use the debugger. Mostly I find trace elements will do a fine job. The debugger is like the heavy artillery I roll out if it's a really tricky problem, if it's really puzzling, I'll roll out the debugger. So this is, if you don't have access to AnyLogic's Researcher or Professional Edition, don't despair. I almost never use it. I do almost everything separately from it, and this I'll use occasionally, but not on a daily basis by any means. Probably about once a year, maybe once every 2 years. Okay, so that's a little bit about when things go bad, because they do. The days are gray sometimes, and if you can proceed in an orderly way, don't flail, don't panic, and use some basic principles, you'll often find yourself getting out of what seemed like a terrible bind quickly. Oh, and also make a copy of the model. Do not debug on the original copy of the model, or it will hamper yourself or cause you a lot of extra work. Okay, some comments there. But I'm still on the narrative, aren't I? The narrative of yesterday. I use these retrospectives to try to throw in additional topics that I wish I had hit at the time. Maybe I didn't have time, or maybe it just escaped me, and it's worth emphasizing. The thing we saw in the afternoon was something of a different character. We introduced this thing called discrete event modeling. And discrete event modeling was a type of modeling that captured the interaction of entities of some sort with a defined workflow in a resource-limited setting, where progress along that workflow, the capacity of those entities to be operated upon within the process, was contingent on the availability of resources. When resources weren't available, people queued up. They waited. So if you know the ultrasound machine was being used for one patient, the next patient waits for it. If the vet is busy in the procedure room for a certain type of procedure, the other patients have to wait for that. So it captures resource-limited flow. Now, yesterday I emphasized, sort of a vet practice where patients come in and they're operated upon and leave. And that's one use of it. But it could also be workflow processes associated with paperwork, registering for some program that provides benefits or what have you when you're at a certain stage of that. It doesn't have to be a thing where you present for care, you're operated upon, and you leave. It could be some more, administrative-oriented process. But we saw yesterday how we could define these with an economy of specification using a set of building blocks in AnyLogic. And we particularly drew from the palette, this process modeling area at the palette. And we saw that we could have these entities flowing through, reserving resources or being allocated resources at certain points, waiting in line, in queues, getting operated upon, and in bulking, potentially leaving, etc. Very simple model we looked at yesterday. It could have been a lot more complex. A person's chance of leaving might have depended on their age and sex, etc. But the point, and underlying condition, but the point is we had a set of operators which were very expressive. We could do a lot with a few operators, and they include things like a source for people just coming in, or entry for those who are coming in from an agent-based model, delays where there's some process undergoing, queues to wait in line, select output. Do you remember where we used this? Select output? Anyone remember? Used it at the very end. That was like when you could either have this happen or that happen. Someone was either cured or not. Do you remember that? You were sent to cure or not. This is a bigger version of that. And seize and release. These were used to seize resources, to allocate a resource like a clinician or an ultrasound machine to a particular patient for a certain amount of time. And then we also had resource pools where you'd have clinicians, or where you'd have ultrasound machines, or where you'd have procedure rooms, or what have you. Those resources could be of several different types: fixed, static resources like rooms, MRI machines, portable resources like portable ultrasounds, or blood pressure cuffs, or what have you, and mobile resources, people, for example, that move around with agency, animals that can move around. So, ladies and gentlemen, we saw this process modeling library was quite powerful. We didn't tap nearly its full potential. One of the most interesting uses of it is to actually show movement in space within a facility where the movement times from A to B are endogenized. What I mean from that is, you don't actually say how long it takes to get from A to B. You just draw the paths by which they can go. It will figure out the path, and based on the patient's characteristics, their speed, and so on, they'll go from A to B more quickly. So if you have a patient in the practice, a vet practice that's a tortoise, it will go slower than a cheetah. Although hopefully neither run around typically within vet practices. So, ladies and gentlemen, within the context of these models, we can associate people with speed and have them proceed from one place to the other. They go back to the nurse's lounge when they're done with their work, or they're put back in the kennel area, they're an animal or what have you. And you can have a very visual depiction of what's going on where the flow, the workflow has endogenized results of how long it takes for people to move from A to B to get resources, etc. The outputs from this sort of modeling, the types of questions, the research questions you ask here, are typically questions about a couple things: waiting times, throughput, number of resources required to achieve a certain goal, or cost associated with those resources, number of service facilities, the location of those service facilities, the location of resources, what resource placement within a given facility would yield the greatest efficiency or throughput or least waiting times, etc. So discrete event modeling, exquisitely good for reasoning about the impact and placement, availability and placement of resources on efficiency and sort of productivity of a given service facility. Now, having built that, we then combined that with agent-based modeling. So we had a population, ladies and gentlemen, and this population had individuals in it who could contract communicable illness, and upon contracting it, they would consider coming in, presenting for care. And after a certain amount of time, they would come in and present for care. And having presented for care, they would then engage in one of these resource-limited processes. And the quality of the care conferred would affect whether they were cured from the infection and from their malady. It was a treatment-mediated recovery, and they would go back to the population in any case. And if they weren't cured, they might re-present for care. So here we have this very interesting interplay, which we see as a real need in many areas of health, between, on the one hand, population health issues, on the other hand, service delivery issues. And often those are undertaken by different sets of researchers. You have the population health folks, public health folks on one hand, and over here you have health service researchers. But the fact is they are coupled. We know that the quality of care delivered within a service facility might have a significant impact on the health of individuals in the population, and conversely, The health of individuals in the population has a huge impact on those presenting for care, and under work pressure issues can lead to adverse impacts on quality of care. If there's a lot of pressure to work quickly because of a large number of people waiting, it may adversely impact the quality of care delivered, the thoroughness of that care, and therefore lead to representations. So rather than treating them as solitudes, you can bring them together. And you can ask, how does placement of facilities, the size of facilities, the staffing of facilities, the availability of resources there affect the evolution of population health, and how does it affect the cost and health burden associated with certain illnesses? And conversely, what sort of level of resourcing, et cetera, do we need within the facilities to adequately address and lower the burden of illness in the population? So these sort of coupled models are very powerful. And while we showed it for one particular instance yesterday of a service for care delivery, it's not the only one. As I say, administrative processes could also be undertaken. So we saw that in the afternoon, and that was our first hybrid model. And we had people presenting for care by taking themselves into a care process. That was also a spatially explicit model with homes, with clinics. People chose to go to the clinic that was closest to them, and we could track on a per clinic basis the patient load. So it could help us reason about where to place clinics, for example. So that was yesterday, and I'm pleased to say, ladies and gentlemen, that today's discussion will build on some elements of that. Okay? So, any questions about my long monologue here on yesterday before we get started for today? No? Okay. So, with that, I will stop this. I want to thank you for your